So let's do a few more examples. However, to just come back to this one, so we have just shown that the map phi from Z cross with multiplication to Z mod 2Z with addition of congruence classes is a homomorphism. But you may ask, is it an isomorphism? So for this you need to know that this map is a bijection. But that's clear, right? There are only two elements here and two elements here. One goes to 2Z minus one goes to 1 plus 2Z. So it's clearly injective and surjective. So as phi is clearly a bijection, we get that phi is an isomorphism. In other words, the group Z cross with multiplication is isomorphic to the group Z mod 2Z with addition. And this brings me back to this discussion about telescopes and indistinguishability between certain objects from the point of view of group theory. If I was looking at these two objects, the units in Z, which were defined using the ring structure on Z, and the rings of congruence classes in Z, for which I use divisibility in Z to define that. But so these are very different objects to start with, right? They even have, like, the operations are very different. Here you multiply things, here you add congruence classes. But if I just look at these two objects from the lens of group theory, if I only use a telescope available to a group theorist, I would look at them through that telescope and I would say, I don't see any difference. If you're only allowing me to use that tool, they look completely the same to me. I can't distinguish them. So from the point of view of group theory, there is no difference between these two groups, between these two objects. Okay? We know that there is difference between them because they arose in totally different contexts. They are really different things. However, not if you look at them only through using the tools available to a group theorist. From the point of view of group theory, they are the same. They look exactly the same, indistinguishable. So this is something to keep in mind, right? What isomorphism means. All the algebraic theories have their accompanying structures. Here the structure is the group structure. And the group structure on both of these objects is the same. So from the point of view of group theory, they're like the same object. Okay? If you allow to look at other structures here, like when you, for example, allow to look at addition and multiplication on Z, and then you extract the units, which are the elements invertible with respect to the multiplication. And then you allow to look at congruences, so divisibility relations in Z, you would say, yeah, this is different from that. But to infer that difference, I actually used some other pieces of algebra other than just the group structure. I used the ring structure on Z to say, okay, that came from elements that were invertible under the multiplication, and divisibility conditions on Z to talk about this. From the point of view of group theory, they are the same thing. All right, let's look at more homomorphisms. So that would be example 6 for us. I'm going to map Z to mu5. Remember the operation here is addition, here it's multiplication, given by phi of A is zeta 5 to the A, where zeta 5 is cosine 2 pi over 5 plus I sine 2 pi over 5. Is this a homomorphism? Quick check now. So want phi of A plus B to be phi of A, phi of B. What's in between them here? Multiplication, because the group of fifth roots of unity is a group under multiplication. So let A, B be integers. Then what's phi of A plus B? By definition, that's zeta 5 to A plus B. And what's phi of A times phi of B? That's zeta 5 to the A, zeta 5 to the B. Are they the same thing? Sure, that's just basic algebra. So this, given by that, is a homomorphism. Is it injective? Surely not, right? 0 and 5 go to the same thing, because phi of 0 is 1, and phi of 5 is zeta 5 to the 5, so also 1. So not injective. Is it surjective? Yep. Phi of 0 is 1, phi of 1 is zeta 5, phi of 2 is zeta 5 squared, phi of 3 is zeta 5 cubed, phi of 4 is zeta 5 to the 4th, and that exhausts already all the fifth roots of unity, so it is surjective. Which is surjective, but not injective. All right, let's look at more of them. Seven. Phi from Z to Z cross Z, given by phi of A is equal to A comma 0. Remember, Z cross Z is a group under addition. Z cross Z is also a group under coordinate-wise addition. So is this a homomorphism? Let's see. What do I want? I want phi of A plus B to be phi of A plus phi of B. But remember, this is a coordinate-wise addition here. So let A and B be in Z. Phi of A plus B, by definition of this map, is A plus B comma 0, while phi of A plus phi of B, what is this? Phi of A is A comma 0, and phi of B is B comma 0. Are they the same thing? Yep, that's how you define addition in Z cross Z. Is a homomorphism. Is it injective? Two different integers are going to go to two different elements like here. So yes, it is injective. Is it surjective? No way. You can never get anything other than 0 on the second coordinate. So, not surjective. Okay. So that was 7. Let's look at something else. 8. Let C infinity be the group of functions f from the reals to the reals that possess all their derivatives, that possess derivatives of all orders. I.e. differentiable functions. Okay, so consider phi from C infinity to C infinity. Oh, the group is right. Possess derivatives of all orders with the operation as we defined before. So f plus g of x is f of x plus g of x. So you're just adding the, so to add two functions means to add their values at every point. Okay, so how am I going to define this function phi? In the following way. Phi of f is going to be f prime. So I am taking the derivative of f. Is this a group homomorphism? Well then, phi of f plus g is equal to, by definition, that's f plus g derivative. But how do you take, what's the derivative of sum? That's the sum of derivatives. Remember, derivative of a sum of function is the sum of the derivatives. So you get this, which is phi of f plus phi of g. So, yep, that's a homomorphism. So phi is a homomorphism. Is it an isomorphism? Well, let's see. Is it injective? Is phi injective? Do different functions from R to R always have different derivatives? No, because if the functions differ by a constant, then they have the same derivative. No, as if c is a constant function, then the derivative of f plus c is equal to the derivative of f, right? And so phi of f plus c would be equal to phi of f. So f plus c and f would be mapped to the same derivative. Is it surjective then? So is phi surjective? So if I start with any function, so let f be in f, be in c infinity. Then is f always phi of some other function? So let's see. I'm going to put a big F here, where the big F of x is defined to be the integral from 0 to x of f of t dt. What's the derivative of f of x, of this big F of x? Well, remember, derivatives cancel integrals. That's the fundamental theorem of calculus. And what you get is just little f, but evaluated at this x. So yes, f is equal to phi of this big F. Right? So note. So phi is surjective. So something that you know from calculus, derivative is actually a group homomorphism. From the group of functions, from the real line to the real line, that possess all the derivatives to itself. But it's not an isomorphism, because it's not injective. Let's look at yet another example. So that will be example 9. Let's look at the following phi. Okay, so first let's make the following note. Note that the positive real numbers R plus are a group under multiplication. Multiplication of real numbers. What do you need to check? If I multiply two positive real numbers, do I get a positive real number? Yes. Is this multiplication associative? Yes, because multiplication inside the real numbers is associative. What's the identity? 1. 1 times any positive real number is that positive real number back. Finally, does every positive real number have an inverse with respect to that multiplication? Yeah, if I take a, the inverse to it is 1 over a, which is also a positive real number. So this is a group under multiplication. So consider the following map. From all real numbers, this is a group under addition. I'm just for this time, I'm gonna put a plus here to emphasize the group under addition. But real numbers are a ring, right? So when I just treat it as a group, I can only treat it as a group under addition. Going to R plus. And here I'm going to put again multiplication just to emphasize that this is a group under multiplication. So I'd like to pause here for a second. I mean, you should pause the video here for a second and think if you know of a map that takes real numbers to positive real numbers, and maybe that map will be a group homomorphism. Okay, so let's solve this mystery now, given by phi of x equal to e to the x. Let's see. So phi of, I don't know, I mean x, maybe let's just say phi of a. I don't know what's a good name for a real number. Phi of a equal to e to the a. So I claim this is a group, this is a homomorphism. So one has that if you look at phi of ab, now I have to do phi of a plus b because that's the operation here. That's, of course, e to a plus b, which is the same as e to the a times e to the b. Oh, but phi of e to the a is phi of a, and e to the b is phi of b. So phi of a plus b is phi of a times b. Addition got turned into multiplication, so this is a group homomorphism. So phi is a group homomorphism. Is it an isomorphism? So is it a bijection? Yes, it is a bijection, and you even know the inverse function to it. Note the inverse function to phi is phi inverse. That will go so the other way. A function that was going to turn multiplication into addition. The inverse of a is going to be the natural log of a. Surely natural log is the inverse of e to the a. So phi is a bijection. Hence an isomorphism. So the conclusion is, right, so the group of real numbers with addition is isomorphic to the group of positive real numbers with multiplication. That's yet another example of this looking through a certain telescope and not allowing yourself to use other tools. If you just use the tools of group theory, there is no difference between positive real numbers with multiplication and all real numbers with addition. To a group theories, they look completely the same. If you just use the telescope, that allows you to look at things through using the tools available to group theories. You cannot tell these two apart. Positive real numbers with multiplication, all real numbers with addition, it's the same thing for a group theories.